Planar graphs. Recap of previous lecture, we have discussed the properties of counting function, chromatic polynomial, chromatic recurrence and further related topics. Content of this lecture. In this lecture, we will discuss planar graphs, that is the plane graph embeddings. We will also cover dual graphs, Euler's formula for plane graphs and regular polyhedra. Embedding on a plane. Let us look into the applications of this concept. Topological graph theory broadly conceived is the study of different graph layouts. Hence, embedding on a plane is widely used in a different field, that is called topological graph theory. Now, initial motivation of this particular putting graph on a plane involved in a famous 4-color problem, which basically was a question that can the regions of every map on a globe be colored with 4 colors, so that the regions sharing non-trivial boundary have different colors. Later motivation of graph embedding on a plane involves circuit layouts on a silicon chip, wire crossing cause problems in layouts. So, the question is asked, which circuit have the layouts without crossings? The two example graphs shown over here are, you can see that there are the embeddings of a graph which has the crossings which are shown by the red dots. Can we redraw this particular graph so that these edges should not cross other than at the end vertices? Similarly, the second graph also has these particular crossings. So, edge crossings are not required in the circuits. So, how we can plot the graph without crossings, and that is called embedding on a plane. Another example is about laying down of gas, water, electricity in the 3 different houses, let us say A, B, C. So, we have to cut through the path and we have to do so that these paths do not cross each other. Now, the question is, can we do this? So, that is, this particular question can be answered if we can draw a K33 graph without edge crossings. We will explore in this particular lecture what are the conditions and what are the different graphs which we can draw on a plane without edge crossings. Hence, they are called the planar graphs. So, the arguments about drawings of a graph in the plane are based on the fact that every closed curve in the plane separates the plane into 2 regions. For example, this is the closed curve. It separates into 2 regions. This is region 1 and this is the region 2. One is inside and the other is outside. So, before discussing a way to make the arguments precise for the graph theory, we will show informally how this result is used to prove impossibility for the planar drawings. So, proposition K5 and K33 cannot be drawn without crossings. So, K33 graph we have seen earlier in the pipeline problem. Let us see whether here it is the proposition says that cannot be drawn without crossings. So, let us see these particular 2 graphs K5 and K33 and we consider the drawings. So, in this particular drawing of, let us say, K5 and K33, there exists a spanning cycle which is shown by the red color. Here also there is a spanning cycle which starts from A and come back to A again, which can be shown over here in another embedding and which is shown as a spanning cycle. Now, if the drawing does not have the crossings, then this cycle, spanning cycle, is drawn as a closed curve. The chords of C must be drawn inside or outside this particular curve. 2 chords conflict if their endpoints on that spanning cycle occur in alternating order. When two chords conflict, we can draw one in inside, the other is outside. What it is saying is that if this is a cycle and if there are two edges which are crossings, then what we can do is we can redraw the other edge. One is inside, the other is outside, hence this crossing can be removed. If there are two chords conflict, we can obtain this particular drawing. Let us see with this concept can we draw this particular drawing, that is K5, using this particular concept. Now here we see that this is the spanning cycle. Let us draw one chord, let us redraw another chord. So far there is no crossing problem. Now to take this particular chord, we can draw from outside, and if we consider this one, we can also draw from outside. What about this particular line? So if we take from outside, this will conflict. So it says that only if the two chords conflict, we can resolve by such a drawing, but if three chords are conflicting, we cannot resolve, they have to cross. So hence K5 cannot be drawn without edge crossing. Let us see about K33 graph. Now this is K33 graph, we have already seen this. This is K33, it can be redrawn in this way also. Let us consider this particular drawing of K33. We have a spanning cycle C, which is shown as the red color. Now let us see the chord. First chord we draw inside, the other chord we can draw from the outside, hence the conflict we can remove. Remaining the third chord, if we draw from this side, even then it will cross to the outside chord. If we draw inside, then it will cross with the inside chord. Hence we cannot draw K33 without the crossings. So therefore these graphs are not planar. So a curve in a drawing, so a curve is an image of a continuous map from 0 1 to r square. A polygonal curve is a curve composed of finitely many line segments. It is a polygonal UV curve when it starts at u and ends at v. A drawing of a graph G is a function f defined on the vertices and the edges union that aligns each vertex a point f v in the plane and assigns each edge with the endpoints u v with a polygonal fu curve. The images of the vertices are distinct. The point in Fe intersection Fe prime, that is not a common endpoint, is a crossing, meaning to say that if let us say this is the graph with a set of vertices and set of edges given, then we require a function f, which is nothing but a drawing of this particular function f. So f will map every point and when there is an edge between these 2 points, so f will draw a curve, polygonal curve. Now if there is a point while drawing the edges E and E prime, if there is intersection, if they are basically in the sense there is a drawing of this is E and this is E prime. So f of E and f of E prime intersection if it is other than the endpoints, if there is a crossing which is not empty, then this common endpoint is called a crossing in this particular drawing. So, it is common to use the same name for a graph G and a particular drawing of G, referring to the points and curves in the drawing as the vertices and edges of G, since the endpoint relation between the points and the curves is the same as the incidence relation between the vertices and edges. The drawing can be viewed as a member of isomorphism class containing G. By moving edges slightly, we can ensure that no three edges have a common internal point, that an edge contains no vertex except its endpoints, and no two edges are tangent. So, if two edges cross more than once, then modifying them as shown below, this can be redrawn so that they will not cross. Hence, we consider only the drawings having these particular properties, that to our best we will consider the drawings without crossings. Definitions for a planar graphs and plane graph. A graph is planar if it has the drawings without crossings. Such a drawing is the planar embedding of a graph. So, a plane graph is a particular planar embedding of a planar graph. So, for example, if this is the graph which is called K4, here there is a edge crossing shown. Now, we can redraw this particular graph using points and curves. So, all 4 points will have, and this straight line or a curve we can draw. This particular edge we can draw from outside, as we have seen in the previous slide. So, we have obtained a planar or a plane embedding of given graph K4. So, this is called a plane graph. Why? Because we have obtained an embedding without edge crossings. So, a plane graph is a particular planar embedding of a planar graph. So, a curve is closed if its first and last points are the same. It is simple if it has no repeated points except possibly the first and last. Planar embedding of a graph cuts the plane into the pieces. These pieces are the fundamental objects of the study here in this topic. Definitions: open set, region, faces. Open set in the plane is a set in the two-dimensional space such that for every point, all points within a small distance from P belongs to U. So, the region is an open set U that contains a polygonal UV curve for every UV which contains in U. The faces of a plane graph are maximal regions of a plane that contains no point used in this embedding. So, a finite plane graph G has one unbounded face, also called as outer face. The faces are pairwise disjoint. Points PQ in two-dimensional space lying in no edge of G are in the same face, if and only if there is a polygonal PQ curve that crosses no edge. In the plane graph, every cycle is embedded as the simple closed curve. Some faces lie inside it, some outside. This again relies on the fact that a simple closed curve cuts the plane into two regions. As we have suggested, this is not too difficult for polygonal curves. We will present some detail of this case in order to explain how to compute whether a point is inside or outside. Dual graphs. A map on a plane or a sphere can be viewed as a plane graph in which the faces are the territories, the vertices are the places, and where the boundary meets. The edges are the portions of the boundary that join two vertices. So, again Let us see that this is the map. So, we can draw a map on a plane or a sphere. This is called a face. These are called faces. This is called face. It defines the territory of this particular region. The vertices are the places. We can define the boundary. Let us say that comprises of the vertices are the places where these boundaries meets, and the edges are the portions of the boundary that joins the two vertices. So, all these particular terms we will see. Now, we allow the full generality of loops and multiple edges. So, from any plane graph G we can form a related plane graph which is called its dual. So, dual of a graph which is denoted as G star is a plane graph. G is also a plane graph whose vertices corresponds to the faces of G. As far as the edges of this dual graph corresponds to the edges of G as follows. If E is an edge of G with face x on one side and face y on the other side, then the endpoints of the dual edge are the vertices x y of the dual graph that represents the faces x y of G. The order in the plane of the edge incident to x is the order of edges bounding the face x of G in a walk around its boundary. Let us see through an example. We can redraw another example, then I will explain it. For example, this is the graph G. What it says that if we draw a dual of this particular graph G prime, so it has the faces. This is face 1, this is face 2. So, the faces of G represent the vertices whose vertices correspond to the faces of G. So, the faces of G will become the vertices of G star. Let us say V1 and V2 are the vertices of as far as the edges of dual graph is concerned. We will draw the edges. If E is an edge, here this is an edge. If E is an edge with face x on one side and face y on the other side, then the endpoints of the dual graph, the dual edge, are the vertices x and y of G. So, you see that V1 is a vertex on the face on one face of G, and V2 is another vertex on another face of G, and there is a edge. So, this edge we have to place between V1 and V2, which will cut through this particular length of this particular face, one side of a face. Now, there is another side of a face and there is an edge. So, we have to draw another edge around that and the third edge. So, this particular red graph, again I will redraw G star, that is the dual, is nothing but V1, V2 has a multiple edges and loops also. So, this example shows it is a multiple edge. Loops will come whenever there is a cut edge. So, every planar embedding of K4. So, this is the K4 and we will see the this is the planar embedding or this is the plane graph of K4. Now, we can see that there are 4 faces. This is region 1, region 2, region 3 and region 4 has 4 faces, and these pairwise share the boundary edges. So, these boundary edges they share. Hence, the dual is another copy of, if we draw the dual of this particular graph. So, for every face there will be a vertex. So, you see that there are 4 different vertices of a dual graph, and these boundaries, that means which are bounded by edge in G, there will be also an edge which will connect those particular. So, that is shown over here, dual graph. So, every planar embedding of a cube similarly has the cube has 8 vertices, 12 edges and 6 faces. The opposite faces have no common boundary. So, the dual of this cube is a planar embedding of k 2, 2, 2, which is a 6 vertices, which is having 6 vertices because it was having 6 faces, and 12 edges are common in both G and its dual, and 8 faces. Why? Because it has 8 vertices. Taking the dual can introduce the loops and multiple edges that we have seen. So, if you draw a paw, this is a paw graph shown by the bold lines. So, here it has 2 faces, 2 regions, 2 vertices will be there in the dual graph, and for every edge there will be a edge in the dual graph. So, you can see that this cut edge will form a loop. Hence, whatever we have discussed, that loops will be formed and multiple edges are also formed. So, here this example shows the multiple edges. This is a loop and this is the multiple edges. In the dual of the paw graph. So, the example shows that the simple plane graph may have loops and multiple edges in its dual. The cut edge of G becomes a loop in its dual graph because the faces on both the sides of it are the same. Multiple edges arise in the dual graph. Distinct faces of G have more than one common boundary edge. Some arguments require more careful geometric description of dual. For each face x of G, we place a dual of x in the interior. So, each face of G contains one vertex and so on. So, with this argument we can show that the dual of a graph, if we take the dual of it, that will be the original graph G. Hence, dual of a dual of a particular graph is an isomorphic to a G graph. Now, we can see that for the given 2 isomorphic graphs, if we take their duals, not necessarily they will be also dual. So, this will be an example of a non-isomorphic dual. So, here we have seen 2 different embeddings of a planar graphs, but if we take their dual, they may be non-isomorphic. So, here we can see that so these particular graphs has 3 different faces. So, in both the cases the dual has 3 vertices. So, vertices. Now, in the embedding on the right side, the dual vertex corresponds to the outside face, has the degree 4. So, this will have the degree 4. Why? Because this is one region, 1, 2, so we can see, we will see that it has the degree 4, but as far as this is concerned, this will not have degree 4. Here in this particular outside case, 1, then 2, then this will form 3, then this will form 4 and 5. It is more than more than 4, and here the dual will be of degree 4. This is 1, we will have 2, then 3 and then 4. So hence both are non-isomorphic duals. Why? Because here the degree is having 4 in this dual and this is degree of more than 4, this is degree 4. So when a plane graph is connected, the boundary of each face is closed walk. When the graph is not connected, there are the faces whose boundary consists of more than one closed walk. How many edges are there? 6 edges are there. As far as its dual is concerned, so the number of vertices in the dual will be equal to the number of faces. So dual will have 3 faces, and as far as, so this is nothing but f of g. So edges are the same as E, that means 6 in this particular case, and the faces of a dual is the same as the number of vertices. So in the original graph, you know that the degree sum formula is applicable. That degree sum formula says that the sum of degrees of that particular graph is nothing but 2 times the edges of the graph. Now here we see that this particular edge E is same as E star, so that becomes 2 E star in that dual graph G. As far as the degree is concerned, here what we can do is that the degree is nothing but the sum of the lengths of the faces. So the sum of the lengths of the faces will become the degree. Hence this particular formula we have derived using degree sum formula. So let us see the proof. What it says, the face lengths are the degrees that we have already shown of the dual vertices. Since E of G is same as E of G star, so the statement 2 times number of edges that we have seen in the previous one, that is nothing but summation of the lengths of all the faces, is twice the number of degrees that we have seen. So this will be going to be equal to the degree sum formula, because E is same as the dual graph and the sum of the lengths of faces is nothing but the degrees of the dual graph. So proposition 6.1.13 illustrates that the statement about the connected graph becomes the statement about the dual graph. When we interchange the roles of the vertices and faces, the edge incident to the vertex becomes the edge bounding a face, and vice versa. So the roles of face lengths and the vertex degrees interchange. We can also interpret the coloring of the dual graph in terms of G. So the edges of dual graph represent the shared boundaries between the faces of G. Hence the chromatic number of the dual graph equals the number of colors needed to properly color the faces of G. Since the dual of a connected graph is the original graph, this means that 4 colors will suffice to properly color the regions in every planar map, if and only if every planar graph has the chromatic number at most 4. So let us see the characterization of a planar graphs. So the following are equivalent for the plane graph, that is the G is bipartite. Second equivalence statement says that every face of G has even length. Third statement says that the dual graph G star is Eulerian. So A will derive A is equivalent to B. So A means G is bipartite, and this is equivalent to saying that every face of G has even length. Now, let us see that the face boundary consists of the closed walks. So, every closed walk contains an odd cycle. Therefore, the bipartite plane graph, the contributions to the lengths of the faces are all even, hence A is equivalent to B. Now, B is equivalent to C. Let C be a cycle in G. Since G has no crossings, C is laid out as the simple closed curve. So, F be the region bounded by the cycle C. Now, every region of G is wholly within F or outside F. If we sum the face lengths for the regions inside F, we obtain the number, an even number, since each face has the length even. This sum counts each edge of C once. It also counts each edge inside F twice. Since each edge belongs twice to the faces in F, hence the parity of the lengths of C is the same as the parity of the full sum, which is even. Now, B is equivalent to C. The dual graph is connected and its vertex degrees are the face lengths, hence B is equivalent to C. Now, we will see the definitions of a outer planar and outer plane graph. A graph is outer planar if it has an embedding with every vertex on its boundary of an unbounded face. An outer plane graph is such an embedding of an outer planar graph. Let us see in this particular example. So, this is a planar embedding. Here we can see that all the vertices are lying on the outer boundary. Outer boundary means there is no vertices is inside this particular bounded region. Hence, it is called a outer planar graph. Outer planar graph, and we have got this kind of embedding. This is called a outer plane graph. A particular embedding, if the graph has outer plane, a graph is outer planar if it has an embedding with every vertices on the boundary of an unbounded face, or a graph is called outer planar if it has an outer plane graph as an embedding. Proposition K4 and K23 are planar but not outer planar. We can see here in the figure that this is K4 and this is K23. So, they are plane graph. Why? Because it follows this particular, it is a plane graph embedding. So, it is a planar graphs, both are planar. Let us see whether it is a outer planar or not. We cannot obtain a outer plane embedding of this particular graph. Why? Because this particular vertex is inside, it cannot cross outside. If it cross outside, then these edges will cross, it will not be a planar. So, there is no outer plane embedding of this particular planar graph, hence it is not an outer planar. Similarly, the other one. To show that they are not outer planar, observe that they are two connected. Thus, an outer plane embedding requires a spanning cycle. There is no spanning cycle in K23. There is no spanning cycle in K23, since it would be a spanning cycle of length 5 in a bipartite graph. That will be length 5 is an odd cycle. Hence, K23 does not have any spanning cycle. However, there is a spanning cycle in K4y because there are 4 vertices. Now, if there is Spanning cycle, let us understand like this. It is a having 4 cycle. Now this is a spanning cycle C4. Now here in to complete this K4, let us assume that one chord will be inside K4. The endpoints of the remaining 2 edges, this particular edge, this alternate along this particular cycle. So this the remaining cycle, so the remaining, so but the endpoints of the remaining 2 edges alternate along it. So this is they will alternate. Hence these chords will conflict, cannot both be drawn inside. So drawing a chord outside separates a vertex from the outer face. So if this particular chord is drawn, then it becomes a planar, but separates a vertex from the outside face, because this will be creating a inner face. Hence this is not a outer plane. To show that they are not outer planar, observe that they are two connected. Thus an outer plane embedding requires a spanning cycle. There is no spanning cycle in K23, hence it would be a cycle of length 5 in a bipartite graph. Now there is a cycle in K4, this cycle is there, but the endpoints of the remaining 2 edges alternate along it. Hence the 2 chords conflict and cannot be drawn inside. Drawing of a chord outside separates the vertex from the outer face. Euler's formula: if the connected plane graph with n vertices, m edges and r regions, then n minus m plus r is equal to 2. This particular formula is well known as Euler's formula for plane graph. So it states for a connected plane graph having n vertices, m edges and r regions, then this particular formula will be satisfied that n minus m plus r is equal to 2. Let us take this particular example graph. This example graph has 7 vertices, 1, 2, 3, 4, 5, 6, 7. It has 9 different edges and 4 different regions, R1, R2 and so on up to 4. So n minus m plus 4 becomes 2, hence this particular equation is satisfied. Let us take another example graph. Here we have 7 different vertices, 8 different edges, 3 different regions which are shown R1, R2 and R3. If we plug into this particular formula, 7 minus 8 plus 3, that becomes 2 and hence it is satisfied. So it is not a coincidence, but for all such connected plane graph will satisfy this particular formula, and this particular formula is called Euler's formula. Let us see the proof by induction on the number of edges. Now, for the base case, let us consider the number of edges as 0. So, if there are no edge present, then it will be an isolated vertex, and that is nothing but a K1 graph. So, in K1 graph, the number of node is 1, the number of edges is 0, and the number of region is 1. So, let us include it in this particular formula. So, 1 minus 0 plus 1, that becomes 2. Hence, this particular formula is satisfied for the base case. Let us see the induction hypothesis. Suppose the theorem is true for all connected plane graphs with less than m edges, where m is greater than or equal to 1. So, now we have to prove for the general case. Now, consider a connected plane graph G on m edges, n vertices and r regions. There are two cases. Case 1 says that if G is a tree, now you know that a tree does not have any bounded region, the number of regions will become 1 for the tree, and if the tree has n nodes, it will be having n minus 1 different edges. So, if we plug in to n minus m plus r the value of m, that is n minus 1, and also the number of region as 1, so this comes out to be 2. Hence, if the graph is a tree, this particular formula is satisfied. Now, let us say that if the graph is not a tree, then it has a cycle. Let us consider the cycle C, and on a particular cycle C there is an edge which is called E. Now, if this edge E is not a cut edge, why? Because if an edge is on the cycle, then in the previous videos we have seen that it is not a cut edge. Hence, E is not a cut edge. Hence, if we remove E from a cycle, then the graph will still be connected. Hence, G minus E is still connected and a planar as well, which has n vertices. Why? Because after an edge is removed, number of vertices will be intact to n values n, and number of edges will be reduced by 1. How about the faces or the regions? Now, we know that if we reduce an edge from a graph, the number of regions will also be reduced by 1. Take this particular example graph. In this example graph, if this edge is removed, then R2 and R3 will be in the same region. Hence, the number of regions will be reduced by 1. So, this graph will have, before removing the edge, it has 3 regions, and after the removing of this edge, the number of regions is reduced by 1, that will have 2 regions. So, number of regions will be reduced by 1. Now, by the induction hypothesis, this particular formula or the theorem holds for a smaller graph, that is G without T. Let us see that if, hence, if we plug in these values over here, n as n and m as m minus 1 and r as r minus 1. So, that becomes n minus m plus r is equal to 2. Hence, this particular theorem is proved. Now, there is a corollary which says that if G is a plane graph with C of G is the number of connected components, then this formula can also be generalized for the disconnected graphs, that is n minus m plus r is equal to 1 plus number of connected components in that particular graph G. Let us take this graph which is having 3 components, 1, 2 and 3 components. Now, this particular graph has 1, 2, 3, 4, 5 different regions. It has 12 nodes and 13 edges. If we plug into this particular formula, so 12 minus 13 plus 5, that becomes plus 5. So, that becomes 4. So, 4 means 1 plus 3. So, 3 is the number of connected components. So, this particular formula is satisfied here in this particular example. Hence, this particular corollary is being taken into an account with the Euler's formula. So, Euler's formula has many applications, particularly for simple graphs where all faces have the length at least 3. Let us use this particular remark as a theorem. So, if G is a simple planar graph with at least 3 vertices, then E is less than or equal to 3n minus 6. Let us prove this. Now, it suffices to consider the connected graph, otherwise we would add the edges. Euler's formula will reiterate and will relate n and E if we can dispose of f. So, the proposition which we have seen previously provides an equality between E and f. So, again if you recall, twice the number of edges is equal to the summation of lengths of the faces, that is given, that we have already seen. Now, every face boundary in a simple graph contains at least 3 edges, that we have already taken. So, therefore, the number of nodes should be at least 3. So, 3 or more. So, that is basically the requirement for this particular theorem. So, let Fi be the list of face lengths. So, this will yield, if we take the sum of the faces, the degree sum or the proposition will give 2E is equal to sum of all faces, face lengths. So, Fi's are all face lengths. Now, you know that every face has length 3, that we basically 3 edges in a simple graph. So, every face contains the length 3 and f is the total number of faces. So, this particular formula, if we substitute for f, then it will 2E is greater than equal to 3f, then f is bounded by 2E by 3. If we substitute here n minus E plus so this becomes 3n minus E is greater than or equal to 6. So, that becomes 3n minus 6 is greater than or equal to E, that we have proved. Now, the another part of this particular theorem says that if G is triangle free, then the faces have the lengths at least 4, hence 2E is greater than 4 times f. So, 2E by 4, that is f. So, if we plug in this value, that is n minus E plus E by 2 is greater than or equal to 2. So, 2n minus 2E plus E is greater than or equal to 4, this becomes minus E. So, this becomes 2n minus 4. So, E is less than or equal to 2n minus 4, that we have proved this particular theorem. Now, we can prove the non-planarity of K5 and K33 using this particular theorem. Now, for K5 we can see that total number of edges is 10. So, if we plug in that particular 3n minus 6 is equal to, that is so E should be less than or equal to 3n minus 6. So, here in K5 n is equal to 5. So, that comes out to be 9. But how many edges are there here present? The number of edges are more. So, it should be 9 or less than 9, since the number of edges are 10. So, 10 is not less than, so it is basically greater than 10. So here the number of edges are more. So edges are more than 9 required for a graph to be a planar one. Hence it is non-planar. Similarly, E should be less than or equal to 2n minus 4, and here in K33 we have n is equal to 6. So that comes out to be 8. So E should be less than or equal to 8, but the total number of edges present is 9. So here also the edges are more than 8 to be planar. Hence this is a non-planar graph according to the Euler's theorem. Now the maximum planar graphs and triangulation. A maximal planar graph is a simple planar graph that is not a spanning subgraph of another planar graph. A triangulation is a simple plane graph where every face boundary is a 3 cycle. Now there is a proposition which will make 3 different statements which are equivalent. So for a simple n vertex graph, the following are equivalent. G has 3n minus 6 edges, G is a triangulation, and G is a maximal plane graph. A is equivalent to B. Now for a simple n vertex plane graph, the proof of the theorem shows that the graph is having 3n minus 6 edges is equivalent to saying that 2E is equal to 3F that we have seen in the previous proof of the theorem. So which occurs if and only if every face is a 3 cycle, and that is nothing but a triangulation. Now B is equivalent to C. Now there is a face that is a longer than 3 cycle if and only if there is a way to add an edge to the drawing and obtain a simple planar graph. Hence this particular condition, that is the maximal planar graph and the triangulation is equivalent. Now planar embedding, we have to see a method to do this. So a graph embeds in a plane if and only if it embeds on a sphere. So given an embedding on a sphere, we can puncture the sphere, inside a face and place a bulb and take this particular embeddings on a plane. This is called stereographic projection, and project the embedding onto the plane tangent to the opposite points. This yields a planar embedding in which the punctured face, this face will be an unbounded face in the plane, and this process is reversible. That means if we can have this kind of plane graph, we can wrap around and we can obtain an embedding on a sphere. This is called planar embedding. Now with this, let us see an Euler's polyhedron formula. So polyhedron are basically here in this particular example, polyhedron which we have defined has 5 faces or have 5 vertices, 1, 2, 3, 4 and 5 vertices are there. It has 8 edges, 4 are in the base and 4 are on the upper, and it has 5 faces. So this is face number 1, this is phase 2, and that will be on the other side phase 3, then the bottom will be phase 4 and outside will be phase 5. Now if V, E, F are the number of vertices, edges and faces of a polyhedron, then again same Euler formula is also applicable, is called Euler's polyhedron formula. Now the applications for regular polyhedra, let us see. Informally we think of the regular polyhedron as a solid whose boundary consists of the regular polygons of the same length with the same number of faces meeting at each vertex. When we expand the polyhedron out to a sphere and then lay out the drawing on a plane using the previous remark, we obtain a regular plane graph with the faces of the same length, hence the dual also is a regular graph. Now let G be a plane graph with n vertices, E edges and F faces. Suppose G is a regular graph of degree k and that all the faces have length L. If we do the degree sum formula for G and for the dual, it will yield to k times n will be the degree sum, that is nothing but twice the number of edges, and that is nothing but the, since every face have, all the faces has length L and there are f number of faces, so LF. Now by substituting n and f in the Euler's formula, n minus m plus r is equal to 2. Here we call it as E and instead of it is f. So let us see, if we substitute for n and f in Euler's formula. So n, if we substitute, 2E by k so instead of f we see 2E upon L is equal to 2. Now if we take E outside, this will become 2 upon k minus 1 plus 2 upon L is equal to 2. Now this is positive and this is positive, E and 2 are positive, hence this entire thing becomes a positive. Therefore 2 upon k minus 1 plus 2 upon L is greater than 0. So 2 upon k plus 2 upon L is greater than 1. So this particular formula we have obtained, and hence this particular term is nothing but 2L plus 2k is greater than KL, and further we can obtain k minus 2 times L minus 2 is less than 4. Again, the dual of two regular graph is not simple, we require then k and L to be greater than or equal to 3. Now suppose k minus 2 and times L minus 2 is less than 4, this also requires that k and L should be less than 5. Therefore satisfying both, k and L should be greater than 3 and k and L less than or equal to 5. So 3, 4 and 5, there are 3 different possible values for k and L are. So k and L will have the possible values are 3, 3, then 3, 4, then 4, 4, 3, then 3, 5, then 5 and 3. 1, 2, 3, 4, 5. There are only 5 possible values of k and L is possible. Now k is that particular degree and L is the length of these particular faces. So once we specify k and L, there are only one way to lay out the plane graph when we start with any face, hence there are only 5 Platonic solids listed below, one for each pair k and L that satisfy this particular requirement, and they are called regular polyhedras. So regular polyhedra, there are only 5 different Platonic solids are possible that are shown over here. So we have considered all k and L different values, which I have told you. There are 5 different pairs K and L, and that comes out to be the number of different edges, nodes and faces, and that is given name to every such K and L pair. That is the first one, when K and L is 3, that is called tetrahedron, and this is the diagram for it. When it is K and L value is 3 and 4, that becomes a cube. So, the cube is shown over here. Similarly, when K and L is equal to 4 and 3, then it becomes octahedron, and they are all regular polyhedra. When K and L is 3 and 5, then it is dodecahedron, and that is shown over here. And when 5 and 3 these values are, then icosahedron, and its figure is shown over here. So, there are only 5 Platonic solids, and that we have derived through, and they are regular polyhedras. Conclusion: in this lecture we have discussed the plane graphs, that is the planar embedding of a planar graph. We have also discussed the planar graphs, dual graphs, Euler's formula for plane graphs, and regular polyhedra. In upcoming lectures we will discuss non-planar graphs. Thank you.